Okay, so today in this talk, we are going to see a special kind of infinite volume hyperbolic three manifolds called almost-Fuchsian, and we are going to study the global geometry of the deformation space of such manifolds. So I'm assuming you are all more or less familiar with hyperbolic geometry, so I'm just going to recall some basic facts, mostly to fix the notation. So I'm going to use the Poincaré model of hyperbolic space. So this means that I'm going to consider the unit ball inside R3 endowed with this Riemannian metric, which is conformal to the standard Euclidean metric with this conformal factor. And this metric has now constant curvature -1 and is such that if you consider points on the boundary of the ball, so on the unit sphere, these are at infinite distance from any other point in the interior. And so we can consider the unit sphere as the boundary at infinity of hyperbolic space. Moreover, you observe that the Riemannian metric endows the boundary at infinity with a conformal structure, which actually allows us to identify biolomorphically the boundary at infinity of H3 with the Riemann sphere CP1. And we are actually going to use this fact throughout the talk. You should also know that in this model, the isometry group of orientation-preserving isometries of H3 can be identified with PSL2C. So PSL2C acts on the boundary at infinity, acts on CP1 by Möbius transformations. And once you know the action of a group element on the boundary, you can also know the action in the interior. Another fact that I'm going to use in the talk is that if you consider these submanifolds, so you intersect the plane x3 equals 0 with the ball, with a unit ball, you obtain a totally geodesic copy of the hyperbolic plane inside H3, and the group of isometries that preserve this totally geodesic copy of H2 is isomorphic to PSL2R. And now PSL2R is exactly the isometry group of orientation-preserving isometries of H2 and is going to act by Möbius transformations, so by isometries on the totally geodesic copy of H2. Okay, so we are interested in hyperbolic three manifolds, so manifolds that are locally isometric to the hyperbolic plane, the hyperbolic space. And we are going to construct these three manifolds by considering representations of a fundamental group of this closed connected oriented surface of genus at least 2 into PSL2C. And the most basic representation we can think of is a Fuchsian representation. So a representation from the pi1 of sigma into PSL2C that actually factors through a faithful and discrete representation into PSL2R. So if we look at how this representation acts on H3, we can see that so it must preserve the totally geodesic plane H2 that I mentioned before. And so if we consider a fundamental domain for the action of ρ0 inside this H2, and then we consider the geodesics orthogonal to this fundamental domain or in H3, so we getting a domain like this, then it's easy to see that this will be a fundamental domain for the action of ρ in H3. And so we see that ρ acts properly discontinuously on the whole H3. And if we consider the quotient, we get a hyperbolic three manifolds of infinite volume, where we can actually explicitly write the metric as hyperbolic cosine squared t times h plus dt squared, where now t is simply the distance from the totally geodesic plane, and h is the hyperbolic metric on sigma with holonomy ρ0. So because ρ0 is discrete and faithful, is a very well-known fact in hyperbolic geometry that any such representation can be realized as the holonomy of a hyperbolic metric on sigma. And one thing I want to remark is that if we consider the limit set of the representation, so the accumulation points of the orbit of a point, we see that the limit set is exactly the boundary of this totally geodesic plane. So in particular, it's a circle in CPU1. Okay, so we are now interested in small deformations of Fuchsian representations. So those are quasi-Fuchsian representations. So are representations into PSL2C with the property that the limit set is a Jordan curve. So it's not difficult to see that exactly because those are small deformations of Fuchsian representations, they will still act properly discontinuously on H3. And the quotient is an infinite volume hyperbolic 3 manifold diffeomorphic to sigma cross R, where now this product will not be a warped product. Actually, you can't write explicitly, in general, the metric on this hyperbolic 3 manifold. And we are going to denote by QF of sigma the space of quasi-Fuchsian representations up to conjugation by PSL2C. So it's a famous theorem by Peirce that the space of quasi-Fuchsian representations is diffeomorphic to two copies of Teichmüller space. It's actually the product of the Teichmüller space of sigma with the Teichmüller space of sigma bar, where sigma bar denotes the same surface but with the opposite orientation. And here I'm considering Teichmüller space as the space of conformal structures on a surface up to diffeomorphisms isotopic to the identity. So the main idea of the proof is that if we consider a quasi-Fuchsian representation rho, by definition, its limit set is a Jordan curve in CP1. And so this Jordan curve separates CP1 into two connected components, omega plus and omega minus, and those are both conformally equivalent to a disk. So if we take the quotient by omega plus and omega minus under the action of rho, what we get is a surface, sigma, possibly with the opposite orientation if we consider omega minus, endowed with a conformal structure. And this conformal structure comes from the fact that CP1, that we have a conformal structure on both omega plus and omega minus. Okay? And so we can construct this map that associates to a quasi-Fuchsian representation rho this pair of conformal structures. And what Peirce proved is that this is a diffeomorphism. So we're actually interested in a special class of quasi-Fuchsian 3 manifolds that actually behave better in terms of surfaces that live inside these hyperbolic 3 manifolds. So let me recall some basic facts about sub-Riemannian geometry, so the geometry of submanifolds inside a Riemannian manifold. So we're mostly interested in the case where the ambient space is a hyperbolic manifold. So M will be a hyperbolic 3 manifold, and I want to study the geometry of a surface immersed inside M. And exactly like when you study surfaces inside it, Euclidean space, you can define the first fundamental form, which is simply the induced metric on the surface. So it's the metric induced by the ambient hyperbolic metric on M. You can define the unit normal. So at each point on the surface, you have a direction normal to the surface with unit length. And you can define the shape operator as the derivative of this normal vector field, where nabla is the Levi-Civita connection for the first fundamental form. And we can define the second fundamental form, which is simply the quadratic form that you obtain by pairing B with the first fundamental form. Okay, and these objects are related by the Gauss-Codazzi equations. So the Codazzi equation tells us that the operator B is a Codazzi operator, so it satisfies this differential equation. And the curvature of the induced metric is related to the determinant of the shape operator in this way. So the curvature of the induced metric is -1 plus the determinant of the shape operator. So if you are familiar with the theory of surfaces inside H3, it's exactly the same Gauss equation. We just have this -1. That's the only difference with respect to the Gauss equation for surfaces in R3. And this term comes from the fact that now the ambient metric has constant negative curvature, -1. Okay, so we say that a surface inside M is a minimal surface if the trace of the shape operator is 0. And the name of minimal surface comes from the fact that this condition arises when you try to locally minimize the area of a surface spanning a certain boundary. So in the case where the surface is a minimal surface, the Codazzi equation tells us that the second fundamental form is actually the real part of a holomorphic quadratic differential. So a holomorphic differential is simply a tensor that is written locally as f of z dz squared, where f is a holomorphic function. And so if you write the real part of Q, you get this 2 by 2 matrix, which is the local expression for the second fundamental form. Okay, so the Codazzi equation, if you write the Codazzi equation in coordinates, in the case where the second fundamental form has trace 0, this exactly tells you obtain exactly the Cauchy-Riemann equations for the function f. And so you deduce that the function f should be holomorphic. Okay, so we say that a manifold, a quasi-Fuchsian manifold, is almost Fuchsian if it contains a unique minimal surface with principal curvatures in -1, 1. So the principal curvatures are the eigenvalues of the shape operator. And we are interested in this special kind of quasi-Fuchsian manifolds. So quasi-Fuchsian manifolds that are actually almost Fuchsian. Okay, so it's a famous theorem by Uhlenbeck that when you have that actually the geometry of almost Fuchsian manifolds can be entirely reconstructed from the embedding data of the minimal surface. So precisely we have the following result. So let's start with a Riemannian metric on sigma and a holomorphic quadratic differential and assume that they satisfy these two equations. So the norm of the quadratic differential with respect to G, defined in this way, is less than 1, and the curvature of the metric is related with the norm of the quadratic differential by this equation. Then there is a unique hyperbolic manifold M and a minimal surface inside M such that the first fundamental form is exactly G and the second fundamental form is the real part of Q. And moreover, this manifold M is almost Fuchsian. So let me give you some ideas of the proof. So the first fact is that if we write the norm of the quadratic differential with respect to G, and f is the local expression for f of z dz squared is the local expression of the holomorphic quadratic differential, we see that the norm of Q with respect to G squared is exactly negative the determinant of the shape operator. And so this equation is actually equivalent to the Gauss equation. And moreover, the fact that the determinant of B is less than 1 in absolute value tells us that the principal curvatures must be between -1 and 1 because the determinant is simply the product of the principal curvatures, which in this case are one opposite of the other because the trace is 0. And so the general theory of surfaces in the hyperbolic space tells us that if we lift everything to the universal cover, we can find a minimal embedding from the universal cover of sigma into H3, which comes together with the representation from pi1 of sigma into PSL to C, because the immersion will be equivariant, with the property that the first fundamental form is just the lift of G, and the second fundamental form is the real part of the lift of Q. So this is simply from the fact that the Gauss-Kodazzi equations are satisfied, and so we can realize these two tensors, G and the real part of Q, as the first fundamental form and the second fundamental form of a surface inside H3. Okay, but we have to lift everything to the universal cover first. Okay, but now the fact that the principal curvatures of the surface are between -1 and 1 tells us that we can foliate the whole H3 by surfaces equidistant to these minimal surfaces, exactly like we did for the Fuchsian case, where we had the totally geodesic plane and we considered surfaces equidistant from this totally geodesic plane. And so in this case, we can actually write explicitly the hyperbolic metric in the quotient, which is given by this expression. And so we see that the manifold is diffeomorphic to sigma cross R. The metric can be written explicitly. And also we see that the limit set of the representation coincides with the boundary at infinity of this minimal surface. And so in particular is a Jordan curve. And so the manifold is quasi-Fuchsian. It's actually almost Fuchsian because by construction, the principal curvatures are less than 1, exactly because we had this condition. Okay, and so you see that the geometry of the quasi-Fuchsian manifold in the case of almost Fuchsian representations is actually completely determined by the induced metric and the shape operator, or equivalently the second fundamental form of the minimal surface. And so we have a parametrization of the space of almost Fuchsian representations via this pair GQ, where G is a Riemannian metric on sigma and Q is a holomorphic quadratic differential with the property that the norm of Q with respect to G is less than 1, and they satisfy these equations. So the curvature of G plus the norm of the cubic of the quadratic differential squared is equal to -1. And we can actually consider this as a submanifold inside the cotangent bundle to Teichmuller space, because we can simply consider the conformal class of G will give us a point in Teichmuller space, and quadratic differentials can be interpreted as cotangent vectors to Teichmuller space. And moreover, almost Fuchsian manifolds contain Fuchsian manifolds because those arise in the particular case where the quadratic differential is 0, and so the minimal surface is actually the totally geodesic plane bounding the equator in S2. So the main result I wanted to talk about is this result by Hodge and Donaldson that says that the space of almost Fuchsian manifolds carries a mapping class group invariant hyperkähler structure. So this means that we can find a quadruple G, I, J, and K, where G is a Riemannian metric on the space of almost Fuchsian manifolds. I, J, and K are complex structures such that K is I times J, and they are all compatible with the metric G. So this means that I, J, and K act like rotations for this Riemannian metric. And moreover, the two forms omega I, omega J, and omega K are symplectic, so are closed and non-degenerate. And moreover, all these structures are actually arise naturally from the geometry of almost Fuchsian manifolds. So in particular, the complex structure I is the natural complex structure that comes from identifying almost Fuchsian manifolds as a subset of the cotangent bundle to Teichmüller space. So you should know that Teichmüller space is a complex manifold, so its cotangent bundle has a natural complex structure. And so this complex structure I comes exactly by thinking of almost Fuchsian manifold living inside the cotangent bundle to Teichmüller space. The complex structure J is induced by the natural complex structure on Teichmüller cross Teichmüller via Beer's double uniformization. So almost Fuchsian manifolds are in particular quasi-Fuchsian manifolds, so we can consider Beer's double uniformization and obtain a subset inside Teichmüller cross Teichmüller. So if we pull back the complex structure on this product by Beer's double uniformization map, we obtain this complex structure J. And the symplectic form omega I minus I omega k, which is now a complex valued symplectic form, coincides with Goldman's symplectic form on the PSL2C character variety. So in a character variety of a surface group, Goldman defined a symplectic form using algebraic methods. And so because we can identify almost Fuchsian manifolds as particular kinds of representations, so as a subset of the PSL2C character variety, we have a Goldman symplectic form restricts to the space of almost Fuchsian manifolds, and actually in this language coincides with omega I minus I omega k. Moreover, the Riemannian metric G restricts to the Weil-Peterson metric on the Fuchsian locus, so on the space of Fuchsian representations. And this metric actually arises naturally in the case of almost Fuchsian manifold because its potential is given by the area of the unique minimal surface. So if you consider the map that associates to an almost Fuchsian manifold the area of the unique minimal surface embedded in these manifolds, you see that these expressions, so if you consider del bar of the area functional, you obtain exactly the form omega j. And this means that the area is a Keller potential for the Keller structure given by J. So that's it for this lecture. So in the next lecture, we are going to see that the same phenomenon happens for a particular kind of Lorentzian three manifolds. So we are going to define these particular kinds of Lorentzian three manifolds, study a little bit their geometry, and we will see that they behave exactly like almost Fuchsian manifolds. And we will then describe the global geometry of their deformation space. And we will find a very rich geometry exactly like in this case. So I'll see you in the next lecture.